I'd like to start thanking the Wagner Prize Committee for this opportunity to be here. Is an honor to be here and to present this project that we have carried out with Sonai, which is the biggest Portuguese food retailer. My name is Teresa Bianchi de Aguiar, and I am here with Jorge Lis, which is the head of the space planning department of the company, and there's nobody better than him to explain the space management problems in the company. So this is the outline of the presentation. I'll start with a brief motivation, and then Jorge will frame the space management at Sonai. And at the end, we'll also present the project implementation and impact. Meanwhile, I will explain the details of GAP, which is the decision support system that we developed for the company. So retailers use planograms to plan the product's placement on the shelves. A planogram is a virtual representation of the shelves where we can see the exact placement of the products as well as its inventory. We call the number of facings the visible items of each product on the shelves. And we see here on the right-hand side the implementation of one planogram in one Sonai stores. Space planning is a mid-term operational activity that is responsible for making sure that customers find what they are looking for when they are searching the supermarket, and also allows retailers to guide the consumers to where they want them to go. It is an activity that connects to many other retail activities, as we see here, such as category sales planning, inventory management, and in-store logistics. But more important than that is the first thing that consumers see when they enter the supermarket. Therefore, it is the face of all retail planning activities. In addition to that, marketing studies have already proven the impact that space allocation has on the increased visibility, consumer awareness, and also on stimulating demand. Therefore, it ultimately leads to better performance. We see here 4 effects that we can recall with space allocation. So we have the first one is space elasticity. The more facings are allocated to a product, the higher the visibility of the product. And also, for instance, you may be aware that the eye level is the premium location of the planograms. But I would like us to focus on the last one, the design complexity. So consumers should understand the logic behind a planogram in order to search for the products, and this is better carried out if we organize products in families and if the families form rectangular shapes as the ones that we see here. In addition to that, space planning also potentiates cost reductions, as the higher percentage of overall operational logistic costs come from handling products in stores. In a Netherlands study that I present here, handling stores assume 38% of overall logistic costs. So we have here high potential to reduce costs if we make sure that the inventory that we have in the shelves is enough to hold through a day or a week. So, but more important than that, it also avoids stockouts. Well, all of these drivers were indeed reported in a study that was carried out to 100 US retailers, where they reported 4 main drivers for space allocation: improve overall profitability, improve overall sales per square feet, reduce stock levels, and improve product availability. Nevertheless, this study also reports that retailers are not experiencing the benefits that they would hope for, and the survey concludes that, and I quote, "Conventional assortment analytics and space tools do not deliver the optimization capabilities needed for success." Now, Jorge will explain why in Sonai's case.
Need to change the micro. Sorry about this, we just have one. So good morning to all, I'm Jorge Lis. I thank you, Mr. Dr. Allen, and the members of the jury for the opportunity to be here. So it's a great pleasure to be here, especially because what we really are seeing here today is a joint work of the academia with companies. And that for Sonai is very relevant, as we work a lot with the guys, with people that really knows about problems and bring some quantitative analysis to our day-to-day life. So first slide I will present is Sonai. So briefly to all of you to understand what is Sonai. Sonai is a holding company in Portugal, a big one of the biggest companies. We have several businesses, all of them related with consumer. So we are the market leader in retail, in food and non-food retail. We also have a presence in shopping centers, and in telecommunications. So all of them are business related to consumers' businesses. So we have three formats. We act in supermarkets, hypermarkets, and convenience store. We have around 400 stores, 500 stores, and we sell $4 billion, which is for the dimension of the country. We have 10 million persons, so it's a very big company with a very big market share, 34% market share, which is not usual in Europe. So as Teresa explained, planograms, which are the representation of the reality in store of the products on the shelves, they follow complex merchandising rules. And merchandising rules are rules that are used to group the products into families in order to the consumers to easily navigate in the store, understand our assortment, and also for us to influence the way they see the products and they buy the products. To do that, we use internal and external sources. Internal sources, we have a very powerful tool, which is our loyalty card, which I can tell you that 75% of the households in Portugal have one, and 90% of our sales are done with the card. So we have extensive data on our consumers. And through basket analysis, we can do a lot of analysis on how the consumers sees the products and how the consumers understands the products on the shelves. We also use internal studies with consumers. We regularly meet consumers. We use eye tracking with the consumers in order to see how they understand the aisles. And also we also are deploying now a technology which is following the consumers with mobile phones. So you are inside the store. I will know where you are, not knowing the specific person, but we just know that there is a device there, and we track all the movements on the store. So in order to understand better how that is done. Another important source to define the merchandising rules are our suppliers. So we are partners with the biggest suppliers in the world, so they have a lot of extensive information about their categories. So they act as category captains and give us a lot of information. With that information set up, we are ready to group the products. So merchandising rules, we are very keen on that. We like to have our linears with a very, very good look and appealing look. So for that, we use a lot of criteria to define the families. So I just give you one example in order to understand what we do. So for instance, flavored yogurts will be first dividing the products vertically in brands, because we know that consumers buy by brand. So the first one is our own brand Continent, so with a good price. Then we'll be organizing in the second criteria by the type of the packaging. So single pack in the bottom and multi-pack in the bottom, sorry. And with this, of course, these criteria will constrain the way optimization models are done. So we are not able to use plain vanilla models because we are constraining a lot this model. So everything is defined, so now we need to allocate faces and depths. So in order to support sales, we need to decide that. And how do we decide that? Simply, the first criteria will be the enough stock in order to support sales. So we forecast sales and we know how much quantity the consumers will buy. But then we'll obviously have agrees with suppliers that you need to maintain certain quotas in the linears. And also, at the end, we will need to maximize our profits. This is not the first one because we cannot just sell what we want. We need to sell everything. So to do this, just to understand the environment, the IT environment, we use a powerful space planning tool from GDA, which is one of the major players, an American company. So that tool will allow us to perform the planogram. So we'll have the products, the shelves, and we'll be putting, with the merchandising rules, the products into the shelves. So, but this task is, although is a high-tech technology, is quite drag and drop technology. So the space manager will be dragging and dropping and mentally deciding the how to allocate products, even the constraints that he knows about the rules. So the person, the space manager, has a very important role on this. Okay. Current softwares do have some generation tools, but as we are too complex in the merchandising rules, we felt that the solutions were not good enough for us. So we decided, knowing all of this information that I provided to you, to do it on our own. So we partner up with the Universidade do Porto, and we try to solve the following problem. What we need to have is something that will help us to reduce the number of manual tasks and increase the number of automatic tasks, so performance by machine power, in order to free our space managers to do more analysis and not to be all day putting products into the shelves. Without, of course, losing the opportunity to optimize the maximum that we can the solution and to standardize the way all our space managers work, so that anyone can enter the organization and do the same thing. Okay, now we'll pass to Teresa that will present us the solution gap.
So, continuing the presentation, in the beginning of the project, SONAI's main concern was to ensure that our planograms were compelling with the merchandising rules that they define. Nevertheless, we were concerned that they were not considering the space effects that we have seen before, and we know how important they are to stimulate demand. Therefore, our proposal to the company was to use a mathematical programming model that was able to use as objective function the space effects that we saw before and as constraints the merchandising rules. In this way, it was possible to balance optimization and automation at all times. So the less rules were defined, the more automatic the process was going to be, and the less rules were defined, the more optimized the planogram would be. And moreover, at all times, it was up to the space manager to decide this trade-off between automation and optimization. I present now an overview of the planogram generation process. So the process starts with the category department that defines the product assortment for clusters of stores. So space managers start by generating a planogram for each cluster, which we call a template planogram or a role planogram. This planogram is then validated with the commercial department to check if it complies with the merchandising rules, and if it is then replicated throughout the whole stores of the cluster. And we see here how similarity the generated planograms, the replicated planograms are with the generated one. So we are talking here of two different processes, first generation process and then replication process. So our first decision was to divide GAP into two different models. The first one is GAP generator and is used during the generation process, and the second one is GAP replicator and is used in the replication process. But before going deep in each of the models, I'd like to say that both processes start with the calculation of the target number of facings for the products. These values are then used as goals while generating the planograms, both in GAP generator and GAP replicator. This is done by using what we call to be a space-to-sales curve that predicts the demand of a product in terms of its space in the planogram. So we can see that it resembles an S shape, and it is based on the marketing studies that we can find in the literature. So the more space is allocated to a product, the higher the demand of the product would be until a saturation point. Our objective was to maximize the profit of the planogram, having in mind this space-to-sales curve, but also to balance the inventory of the products on the shelves in order to make sure that the replenishment was triggered at the same time. So we divided the space-to-sales curve into intervals of day supplies values, number of days that the products hold on the shelves, and we developed a mixed interprogramming model that uses piecewise linearization in order to deal with the nonlinearity of the space-to-sales curve. Our objective is then to make sure that all products are inside each day supply interval. Going now into the gap generator module, our objective was to generate fully defined planograms, having in mind the assortment and also the merchandising rules that were given as inputs. So our decisions were the number of facings and also the location of the products on each shelf. For that, we had to make sure that we were complying with the merchandising rules that we've seen before, and make sure that they were forming rectangular shapes and also with the directions that we saw. So we've seen up until now the importance of merchandising rules. So we capture this relation between the families using a direct acyclic graph as we see here. So we start with a dummy node in the upside of the graph that is connected to the families of the first level. So in George's example, the first level families were the flavor and the creamy yogurt, just to give an example. So then each family of the first level is connected with its downstream families and so forth until reaching the product level. So if we think about this problem, the highest challenge is to determine the sequence of products on each shelf. So an initial approach would be to use a network problem where we associate each product with a node and determine the sequence of products on each shelf. Nevertheless, this would make the model intractable, especially for a practical case than this one. Therefore, we used an innovative network problem that uses multi-level networks on each shelf. So we start with a network with the families from the first level, and we sequence them on the shelf. Then, for each upstream family, we developed a network with its downstream families and also decided the sequence that they are going to have on the shelves. And we continue further down until reaching the products. Then, at the end, if we join all networks together, we obtain the product sequence on the shelves. We also use commodity flow constraints in order to avoid subtours. Well, this is the complete formulation for this problem. Besides the sequencing constraints that we have seen so far, we also have our objective function and allocation constraints that make sure that we try to obtain the target number of facings that we've seen before. And at the end, we have the product grouping constraints that make sure that families are aligned between shelves in order to form those rectangular shapes that I've been talking about. In order to solve this problem, and because the execution times were not yet what we were hoping for, we embedded the formulation in a math heuristic that sequentially solves a sequence of sub-problems that take advantage of the hierarchy of the product families. So we start by solving the families from the first level and continue so far until reaching the product. We do it considering the whole formulation at all times, but the decisions that we don't want to focus, they are relaxed. We compared our formulation with the state-of-the-art model, the only one that we found that were generating fully defined planograms, and we were able to obtain 26 more feasible solutions in 31% less time, which was very good for us. But our math heuristic was even able to improve these results by obtaining 80% reduction on execution time and also obtain better solutions for 20% of the cases. So up until now, I've talked about this balance between automation and optimization, and I would like to show you an example. So on the top of this slide, we see a manual planogram that was handmade by one of the space managers of SONAI. And then we see two planograms that were generated by GAP. In the first one, the space manager fully defined the merchandising rules, and we see that the planogram is quite similar to the manual planogram. So in here, we are in the most extreme automatic version of the problem. Nevertheless, if the space manager relaxes some of the rules, then it starts heading towards optimization and obtains some interesting solutions that he can evaluate and check if they can be used on the stores. Going now into GAP Replicator, its objective is to generate store-specific planograms, having in mind a generic planogram that receives as inputs. So the objective is to determine the new value for the number of facings, but it has to make sure that products keep the same relative position and are also aligned in their families, so that the image of the planogram is the same as in the generic planogram. So this may appear a simplistic problem compared with the generation problem, but it was challenging because planograms, when they are implemented in stores, they actually have some irregularities, as we see here. So most often we find some misalignments between the shelves and also some shelves missing that we had to handle in this formulation. So besides the objective function and the allocation constraints that we've seen in the previous formulation, we also make sure that the full planogram is occupied. So we are explaining on reducing the planogram, and we want to occupy the whole new planogram. And we also make sure that the product's positioning and the family alignment compel with the generic planogram. In order to ensure the scalability of this approach, we also used a MIP-based heuristic that has three main phases. In the first phase, we create an initial solution that only ensures that all products are present in the planogram. Then, in a planogram filling phase, we iteratively add the remaining product facings by increasing order of their supply values in order to balance those values. Once the planogram is complete, then we pass to a planogram improvement phase where we allow the removal and insertion of new faces in order to obtain better solutions. So the first thing that I want to say is that we are introduced here an innovative OR application, but we were also able, through the MIP-based heuristic, to obtain quite amazing results. So we were able to reduce on average 88% of the time, and with an optimality gap of 0.1%, almost 0.2%. In here, we compare handmade planograms with our new planograms, and we check that in terms of day supplies values, we are actually reducing the deviation between the products and also the average value. But we also check by the size of the balls that the higher the number of merchandising rules, the less the impact of balancing day supply values, because we are more constrained to obey to the merchandising rules. Up until this point, I've talked about the optimization part of the decision support tool that we call the gap generator. This application connects with a solver that is able to solve our models that we generate throughout the generation process. And they are solved using FICO Express solver that was acquired by the company. We also have an interface which we call the GAP interface that is the connection with the space manager. Our main interface is the generation manual that allows space managers to tune the merchandising rules that he wants to see in the planogram. But more important than that, the space manager is able to visualize and analyze the data using the same software that he was used to use. So we connect with the space planning software, and our planograms can be visualized there. We start this project with shelves, so we were generating planograms with shelves, but now GAP supports multiple types of fixtures. So besides shelves, we also generate planograms with pegboards, with tables, with bins, and so forth. Now I will pass the word to Jorge to explain the project implementation and impact.
Okay, we'll now present the project itself and the results. So the first important result is, as we are doing a work of replacing a lot of manual work by machine work, is always the danger of the persons of the team will be felt replaced by a machine. So the first thing that we did is explain very well to all the team the benefits of the project, that we will be reducing the time they pass in front of the software, putting the products in the shelves, but they will gain a lot of time to analyze and to criticize the solutions that we are getting, so adding much more value. So the solution now is used in every day and by every person of the team. So that's a success in the first success that I want to share with you. The second one is that in terms of production of the planograms, we achieve fantastic results. So we are able to reduce from moment zero to the moment we produce the planogram more than 50% of our time. So the process is quite different, but at the end of the day, we are reducing more or less to half the time we used to have to do the planograms. And the planogram coverage, as Teresa explained briefly before me, is now 80% and improving because we are adding more types of equipment to the software. For us is a software, it is a decision model for Teresa. So in terms of profit maximization and stock reduction, we achieve also very good results. So far, when we have a low customization, low merchandising rules, we are able to get to 1.5 improvement on sales. Of course, sales in retail the effect on sales on retail is not easy to calculate because we live in Portugal at a deflating period where everybody is crazy about promotions on price. Price is the key variable. So, but when we are able to stabilize two planograms, the old one and the new one, we can see that sales are increasing, and more than that, also complexity of the planogram is reducing, so stock is reducing, so our persons in the store will have less time to fill the shelves. Also, the space that we occupy is more with GAP, so we came from a 94% occupation of space, so nowhere in the shelves, to a 96% occupation of shelves. That is also important because more products will be in the shelves. Execution times are fantastic, so with high customization we'll get 7 minutes, with low customization 2 minutes to get a planogram, so that results are amazing. So in terms of the project started 2 years ago. The key success factor was a huge team that we put in place from the university, from ourselves. The regular meetings with all of us, so all the persons who were involved would meet regularly in order to solve the problems that were appearing. We get out with 2 solutions, so splitting the problem into 2, that helps a lot. And we made intensive training to everybody. So now Teresa, concluding.
Okay. In the beginning of the presentation, Jorge divided the project into 3 main axes. optimization, standardization, and automation. And we've seen throughout this presentation that we were able to target and to improve both the three dimensions. So we may say that CAP is a successful application of analytics to enhance shelf space management at Sun IMC. Moreover, as it uses merchandising rules that are defined on the fly, it can be used in other retailers. But throughout this presentation, I also stressed the impact that we have on the state-of-the-art of this problem. So first of all, we are generating fully defined planograms with our models, which is not for sure common in the literature, that only tackles the space allocation, deciding only the number of facings. Moreover, we are bringing to academia the focus on merchandising rules and how important they are while developing the planograms. All this work resulted in 3 technical papers that you can consult in order to be more aware of the technical details. I would like to finish showing the whole team of the project, and I'm glad to say that there are many of us here today in order to present this work. Thank you very much.